All right, guys, so we're finishing going over the review sheet today. Your test is tomorrow. Part 1's tomorrow. Part 2 is Thursday. There are 2 parts to it. So, where we left off was with 25 and 26.
May I have your attention,
Find.
please? All employees there are bags of apples in the teacher's workroom for you. Thank you.
Hey. Find all the factors, the rational zeros. So, plus or minus P over Q. P is the factors of the constant term. Q is the factors of the leading coefficient. Constant term is our term without a variable.
Wait, the P is the what?
The factors of the constant term, our term without a variable. Q is the factors of the leading coefficient. So our constant term in this case is 27. So we need to find all the numbers that multiply together to give us 27. And a good one to start with is 1 and 27, 1 in the number itself. Then we could go through our next numbers. 2 is not divisible by, or 27 is not divisible by 2. 3 is, it'd be 3 and 9. 4 doesn't work, 5 doesn't work, 6 doesn't work, 7 and 8. And as you go through and do that division, I would be checking and seeing what the results are, because we could do in the calculator 27 divided by 2. That doesn't work. 27 divided by 3 gives us 9. 27 divided by 4 is 6.75. 27 divided by 5, 5.4. But if you notice what we're getting, what multiplies together to give us 27 is now reached. They're the same, 5 and 5.4. It means that 6 and whatever it's going to multiply by is less than that. We're done. If they were going to show up, they would have showed up by this point. Now, so the only factors of 27 are 1, 3, 9, and 27. Factors of the leading coefficient are going to be the factors of 9. Well, we have 1 and 9. 2 is not a factor of 9, but 3 is, and it would be 3 and 3. That's it. Those are the only factors of 9. Now, just because, now, not just because, but since 3 is a factor twice, we're not going to list it twice. Because any of the factors we get for one of the 3s, the other 3 is going to have the exact same solution set for our plus and minus. If it repeats, we're not writing it twice. Questions on how we found the values for P and Q? P is the constant term, our term without a variable. Constant term is, by definition, does not have a variable. Mm-hmm.
How did you find the leading coefficient?
So leading coefficient is the number in front of the variable with the biggest exponent. Mm-hmm. Now, when we start finding P over Q, I always start with one value of Q and divide every P by it. So we're going to start off with 1 divided by 1, which is just 1. Well, anything divided by 1 is the number itself. So really with our 1, we're going to get all the factors of P back. Plus or minus 1, plus or minus 3, plus or minus 9, and plus or minus 27. That's just divisibility of 1. Then we'll move on and do the same thing with 3. So the first one we have is plus or minus 1/3. Now we could do these in a calculator and make sure that they don't reduce, because if we move to the next one, 3/3, well, 3 over 3 is going to reduce to 1. Yes? Is 1 listed? We're not listing it twice. 9 over 3 is going to reduce to 3. It's already listed. We're not going to write it again. And 27 over 3 is going to be 9. And we could do these in the calculator. I can say 3 over 3 is 1. 9 over 3 is 3. 27 over 3 is 9. The calculator will do the reduction to reduce this for us. If it's already listed, we're not writing it a second time. Our last factor of Q is 9. So we can do 1 over 9. So plus or minus 1/9. That doesn't reduce, it doesn't simplify, so it's still just 1/9. Now, the next one would be 3/9, which is 1/3. We already have it. 9/9 is 1. 27/9 is 3. If it gives us something we don't already have, we have to list it. And since we finished ninths, there is no other factor of q. So 1, 3, 9, 27, 1/3, 1/9, and the negative versions of those are all the solutions. You have to have the plus or minus. We need both. We need the positive 1, negative 1, positive 3, negative 3. 1 over 3. Yep. Yeah, they're the only ones that change because 3/9, 9/9, 27/9 all reduce to 1/3, 1, and 3. If they're already listed, we're not listing them a second time. Yep. Any other questions on the rational zeros? We good with these here? Okay. Descartes' rule of signs. Descartes' rule of signs. This tells us the number of possible positive zeros, the possible negative zeros, and based off that too, we can determine the number of complex. Now, looking at this first problem here, number 27, the degree is 5. So that tells us that the number of solutions that we should have for this is 5, because the degree is equal to the number of solutions. The number of solutions is equal to the degree of the polynomial. Degree is 5, so the number of solutions is 5. Now, to determine the number of positive zeros we can have, we count the number of sign changes from term to term. So we go from x to the 5th to x to the 4th, it's going from positive to negative, so that would be 1 sign change. From x to the 4th to x to the 3rd, we're going from negative to positive, so that would be 2. X to the 3rd to x squared, we're going from positive to negative. X squared to x, we're going from negative to negative. So since there is no sign change, we don't count it. We're only counting the sign changes from term to term. And then from x to our constant, it's going from negative to positive. So the most positive zeros we could possibly have is 4 or an even number less than it. So if we wanted to list out all the possible cases, we could have 4, we could have 2, or we could have 0 positive solutions. Now, how they connect with the negative and complex, we will have to list out. Now, the negatives. F of negative x. So to find the negatives, we have to plug negative x in for every x and simplify. Now, to keep it on a simpler way to look at this, because we're mainly focused on the sign change from term to term, but we got to plug that negative x in first. And when we looked at this originally, and we've talked about this before, to determine how this is going to affect each term, we look at the exponent attached to the variable. If the exponent's odd, that negative x is going to be negative after we apply that 5th power. So for x to the 5th, because it's an odd exponent, we're going to have that negative come out of the x to the 5th, which is going to make that 6x to the 5th go from positive to negative. We're adding a negative to it. Now the x to the 4th, 27x to the 4th. When we apply an even power to this negative x, that negative is going to become positive, which means whatever sign was with the 27x to the 4th is still going to be with it. Because the odd powers, we're adding this negative exponent to the coefficient, which is changing the sign. Even powers, we're adding a positive sign to that leading coefficient, which is doing nothing to it. Our next one is 56x cubed. Is that exponent odd or even? Odd, so the sign has to change. It was positive, it's now going to be negative. Our next term is x squared. Exponent even, so the sign stays. If the exponent's even, the sign stays the same. If the exponent's odd, we've got to change it. We only have two terms left. The next one we have is 36x. What is its exponent? 1. 1 is odd, so we have to change it. Doesn't change the plus. Our last term is 40. Is there a variable? Nope. So we don't do anything with it. There's no odd even, it's just plus 40. Because we did not plug a negative x into it, so there's no way you could change at all. So especially finding the negative case, this negative f of negative x. If the exponent's odd, change the sign. If the exponent's even, leave it alone. And then all we have to do is count the sign changes from term to term. So we're going from negative to negative, no sign change. Negative to negative, no sign change. Still negative to negative, no sign change. Negative to positive, positive to positive. So our negatives, we have 1. Questions on how we found the number of positives and negatives. Now we need to arrange these. So positive, negative, complex. Really, we're grouping how many positive, negative, and complex can show up in a solution. Each of the rows is one of options that we could have for our solution set. The set of numbers that makes the function equal 0. Now I always start with the most of each, because we can have 4 positives and 1 negative. If I have 4 positive solutions and 1 negative solution, how many total solutions would we have? 5. The degree is 5, so we should have how many solutions? And if I have 4 positive and 1 negative, we do have 5 solutions, all 5 solutions, yes? So are we missing any from the total? So the number of complex has to be 0, because if I have 4 positive solutions and 1 negative solution, I have all the solutions. There are no missing. There's none that we have to find left. Now from here, I would start subtracting from the negatives just to make sure I have every arrangement of the positive and negative. But if I take a group of 2 away from the negatives, because it's this amount or less than it by an even amount, well, what is 1 minus 2? Negative 1, yes? Can I have a negative group of numbers? No, we can't have a negative amount. So the only place I can really take the 2 away from is the positives, because we said we could have 4 positives, 2 or 0. So the other option for this set is we can have 2 positives and 1 negative. How many solutions do we have with that? 3. How many are we supposed to have? How many am I missing? So the number of complex has to be 2. Again, we still can't take any away from the negatives, but I can take one more group away from the positives, because it could be that we have 0 positives and 1 negative. Well, if I have 0 positives and 1 negative, we only have 1 solution. How many are we supposed to have? 5. So how many are we missing? 4. So the number of complex is 4. There are no positive, negative options. This is it. So it's 4, 1, 0, 2, 1, 2, or 0, 1, 4. That's it. Yes. I will also say that the number of complex has to be an even number.
How do you know which positive?
Or what the actual positives are going to be,
Yeah.
we have to actually look into it. We actually have to use the rational zeros, graphing, our other methods to figure out what those are. But the reason that this is nice is if I say I graph it and I see that it crosses the x-axis on the positive side in 3 places, I know there has to be a 4th. I don't have 3 positives as just a solution. I can either have 4 or I can have 2 or I can have 0. So if I see that it crosses at least once on the positive x-axis, I know it has to cross it again, because I have to have 4, 2, or 0. It starts giving me more ways to see what the answers are. It doesn't tell me what the actual positives or the actual negatives are. It tells me that they exist. Does that make sense? Especially with the rational zeros, as I start trying solutions, I know that one of them has to be negative. No matter what setup we have, in all three options we have one negative solution that has to show up, which is fine. And I do the rational zeros and we see that, I'm just going to throw one out there, it'll say -2 worked. That means every other possible negative rational zero that we have will not work. Because no matter the solution set, in all of them we only have one negative solution. So once I find it, I don't have to look at any other negative solution because they won't work. Does that make sense? Essentially, it gives us a way to see what the solutions are and what they can't be. If I find one negative, well, it's either 4 positives, 1 negative, and 0. I found one negative. Any other negative, like we had with this here, oh, -3 works. That means -1, -9, -27, -1/3, and -1/9 are gone because we can only have one. So we start using the rational zeros and these here as ways to find solutions, as ways to help us get to the answer. Does that make sense? The formula ended up, this does not tell us solutions. It tells us what type of solutions we should be looking for. Or to get the table, no, but when we solve, yes.
I just didn't understand how you got a positive. It's gonna go down as even. Like, yeah, you can go down.
So it's 4. It is the number of sign changes for less than it by an even amount. So the smallest even is 2. If there are 4 sign changes, so the most we can have of the positive zeros is 4, or less than it by an even amount. So less than it by 2, or really less than it by 4. So we keep decreasing it by 2 till we can't. So the number of possible positive zeros is 4, 2, or 0. And it gives us an idea of what to look for in solutions. For the most part, and especially on the test, you're just going to look for the table. It's not actually asking you to solve that one. Questions on our rule of signs? 29 through 34, we want to solve. We're actually solving. And for most all the solving, I would just start by graphing. So for 29, first thing I do is grab the graphing calculator and hit y equals. And we just want to type the function in. So we have x to the 5th minus 20x to the 3rd plus 20x squared minus 21x plus 20. We want to type the whole function in and hit graph. We want to type the whole function and hit graph. Now, because the degree is 5, we need 5 solutions. We are going to have 5 solutions. We're going to have 5 values of x that make this function equal 0. Yes, ma'am. Y equals. Now, number of zeros that we should have is 5. But at minimum, we need 3. We need 2 less than the degree. Since the degree is 5, we need at least 3. You need a variable in front of the 5. You need that x in front of the 5th power. If you do get an error, do ask. But once we graph it, we should get something that looks like this here. So we do have 3 spots. It intersects the x-axis. We do have 3 zeros. So the three values of x that make this function be 0 are negative 5, 1, and 4. Second graph gives us the table. Graph just gives us the graph. And again, we're looking for the values of x that make the function equal 0. Now, if we had gotten 5 solutions, we're done. Because the degree is 5, the graphing calculator told us all 5 solutions. We aren't looking for anything else. If it tells us 4, we're going to do synthetic division until we get down to the last one. Solve from there. Or here, it gave us 3. We're going to use those 3 solutions to get it to a quadratic and solve the quadratic. Now, the first one of these that we pick really doesn't matter. We could do negative 5, 1, or 4. I'm just picking negative 5. Now, the numbers across the top, we do have 1 for x to the 5th. Now, because we don't have an x to the 4th term, we have to fill it in as 0. We will have negative 20 for our x cubed, 20 for our x squared, negative 21 for our x, and 20 for our constant term. We bring the 1 down. Now we're going to start our multiplication, multiplying and adding as we work through the synthetic division. So the first thing we're going to do is take that number in the cubby and multiply it by the number below the line. So negative 5 times 1 is negative 5. Then we're going to add those two numbers together. So 0 plus negative 5 is, well, negative 5. Then we're going to multiply that number with the number in the cubby. So negative 5 times negative 5. 25. Our negative make a positive. 5 times 5 is 25. Then we'll add again. Negative 20 plus 25 is going to be positive 5. Now we're going to multiply that positive 5 by our negative 5 in the cubby. Negative 5 times 5 is negative 25. And again, we're going to add those two together. 20 plus negative 25 is negative 5. Now we're going to multiply again. Our negative 5 in the cubby times the negative 5 below the line is going to give us positive 25. Now we're going to add negative 21 and positive 25, which is 4. And negative 5 times 4 is negative 20. And 20 plus negative 20 is 0. Now we're going to do this again, but with our next solution of 1. So we're going to multiply the 1 in the cubby by the 1 below the line. And our, yes, 1 times 1 is 1. Then we're going to add the negative 5 and 1. Negative 5 plus 1 is negative 4. Then we're going to multiply that negative 4 by the 1 inside the cubby. 1 times negative 4 is negative 4. Okay. Now at this point, we're going to add 5 plus negative 4 is 1. 1 inside the cubby times the 1 below the line is 1. Negative 5 plus 1 is negative 4. And 1 times negative 4 is negative 4. And 4 plus negative 4 is 0. And the last solution that we have that we were given is 4. So we're going to do this one more time with 4. Now our 4 in the cubby times the 1 below the line would be 4. Negative 4 plus 4 is 0. 4 times 0 is 0. 1 plus 0 is, and lastly, 4 times R1 is, and negative 4 plus 4, 0.
Like, I thought you were supposed to do it by the bottom, like 1 plus 0 is 1, but with that move over, it'd be negative 4 plus 1.
So the 1 drops below the line. So the 1 plus 0 would give us 1. We put it under. We multiply that 1 underneath by the 4 here to give us that 4.
Oh, yeah.
Yep. So it could work that the other two solutions are one of the ones we have already. There's a good likelihood they could be, but not quite. Because if we get down to a quadratic, and especially that middle term is 0, I'm going to go on and fill the variables back in. Because if we fill the variables back in here, the first one is our constant term. Our 0 is our term with x. The other one is our term with x squared. Telling us that we have x squared plus 1 as our final expression. And we are solving it, so it is going to be set equal to 0. If we don't have a middle term, if we don't have a number times x to the first power, square root method. Get the x squared by itself. Because if we subtract 1 from both sides, the left side becomes just x squared because our positive 1 minus 1 is 0, leaving us with x squared. The right-hand side, we have 0 minus 1 is negative 1. And once we get the x squared by itself, we can square root both sides because the square root of x squared is just x is equal to plus or minus. Whenever you take the square root of both sides, we have to put the plus or minus. Square root of negative 1 is, by definition, I. I is the square root of negative 1. The other way we could do it is we could take the negative out as I, which leaves us with, because this negative is going to come out as I, and I'm taking the square root of, and the square root of 1 is 1. So 1I or just I. Either way work. So the other two solutions are positive and negative I. So all the solutions, the 5 solutions for this here are negative 5, 1, 4, I, and negative I. We have all 5. Here's 5. Because negative 5, 1, 4, positive I, and negative I. Because positive and negative I, plus or minus I. There are only 4 terms technically listed, but the plus and minus gives us an easier way. So we don't have to write I, comma, negative I. We can just say plus or minus I. Simpler way to write it. Not really, but it is. Yes. Questions on 29? Because if we only have x squared, we don't have an x term, we can get the x squared by itself, square root, and be done. If we have that middle term, that term with x, we have to use quadratic formula, completing the square, other methods. Square root method says get x squared by itself, square root both sides. And we're done. Questions on 29? Let's look at 30. X to the 4th minus 6x cubed plus 7x squared plus 6x minus 8. How many solutions am I looking for? 4, because the degree is 4. First place I would go is graph it. If it's going to give me zeros, might as well graph it. Now, since the degree is 4, we want at least 2 less than the degree, which means I want at least a degree or at least 2 zeros. If I can find 2 solutions, we can get it to a quadratic, and it's solvable from there. x to the fourth minus 6x cubed plus 7x squared plus 6x minus 8. Because if I can get 2, we can get it to a quadratic. We have ways to solve quadratics. Square root method, completing the square, quadratic formula. If we get 3, we get it to a linear. Add, divide, we get x by itself. If we find 4, we're done because there are only 4 solutions because it is a 4th degree polynomial expression. And as we look at this here, how many times does it cross that x-axis? 4. We expect it to cross at most 4 times because it is a degree 4. We have 4 solutions. I can go second table and see if I do find 4 nice values of x that make this function equal 0. And then we see here at -1, the y value is 0. Second graph. At 1, the y value is 0. At 2, the y value is 0 and 4. So it tells us -1, 1, 2. It tells us these here at -1, 1, 2, and 4. When x is these values, the y value is 0, yes? How many solutions did we find? How many was I looking for? Do I need any others? So those are the solutions, yes? So we are done. -1, 1, 2, 4. That's it. Because what's the degree? So the number of solutions should be, how many do we have? So we are done. Yep. Because before the fundamental theorem of algebra, where we could say that the number of solutions equal to degree, then we would have to do synthetic division and break it down and see, did we actually find them? But now that we have, and we know, like for 31, that the degree is, because here we can go about finding it. We're going to skip 31. We'll look at this one here because I will tell you this, every single one of them, if we do have to solve for the rest, square root method is going to work. You will not have to do one by complete or the quadratic formula or completing the square. I did that on purpose. Let's look at 33. 3x cubed plus x squared minus 38x plus 24. Again, I'd graph it. We'd hit y equals. Now we do need to clear this out. And we're going to type this in. 3x cubed plus x squared minus 38x plus 24. We're going to type, yeah, 33. So we do see it crosses the x-axis in 3 spots. 2 of them look nice. 1 of them looks like it's probably not going to be a nice number, a nice integer anyways. So we have -4 and 3 for sure. Now you might have to scroll up or down to find it. That's why I do hit graph first. I look at the graph to give me an idea of where on the x-axis it's going to be. Because we can count the dashes and go over and see that the one on the left, 1, 2, 3, it's going to be over around -4. And the right, we're going over 3. So if it's not showing up in the table, we can look at the graph to kind of point us in the direction to get the table to contain that value, either going up or down. Now, when x is -4, the y value is 0. When x is 3, the y value is also 0. Now, the degree of this is 3, so we should have how many solutions? 3. How many do we have? 2. So since we are missing a solution, we are going to need to do synthetic division to find it. Now, this is a little bit nicer because the minimum we needed for this here was 1. Because the goal with all of our methods for solving is to get us down to a quadratic. If we can get down to a quadratic, we can use square root method, completing the square, quadratic formula to solve from there. if we get 2, we get to a linear equation of a line. And if we get equal to the degree, we're done. Yes?
Like, okay, I'm not understanding how, like, all the exact same. We had all the steps, but then we put a problem 30. All we had to do was find
What's the degree?
the solution on this one.
Yeah.
3.
So this one where we had a lot of steps, what's the degree for it? So we have to find 5 solutions. Well, it didn't tell me only all 5, it only told me 3. So we have to, because when we do the synthetic division, we're removing a solution. We're removing a factor, so it's taking the degree down, it's making it easier to solve. So here, I had to remove 3 solutions from it to get it there. Here, it already told me all of them. I don't have to check, I don't have to do anything. Here is going to be less work because we only have 3 solutions, so we found 2 of them, so we're only doing the synthetic division twice to solve. Now, when we do the synthetic division, our 3 times 3 would give us 9. 1 plus 9 is 10. 3 times 10 is 30. Negative 38 plus 30 is negative 8. 3 times negative 8, 24. And 24 plus negative 24 is 0. Now, at this point here, we could solve. Because it was a degree 3, we removed a solution, so now it's a degree 2. It's a quadratic, we can do that. But I know for certain that negative 4 is also a solution. If I can get it down to a degree 1, it's going to be easier to solve than a degree 2. So we can do this again. Negative 4 times 3 is negative 12. 10 plus negative 12, 10 minus 12, negative 2. Negative 4 times negative 2 is positive 8. And 8 plus negative 8 is 0. So when we add the variables back in, what we're doing is we look at it and see what we have. Now, since we're only dividing by the one term, the last number is always the remainder. So, constant term. When we go outside the remainder, the first one, we could say, realistically, it's the term without a variable, the variable to the 0 power, and we're increasing the power by 1. I just think of it as that first number outside does not have a variable. The one next to it, the one after it going to the left, would have a variable to the first power. If there's a number in front of the 3, it would have that variable to the second. If there's a number in front of it, it would be to the third. Number in front of that is to the fourth, because as we move one number to the left each time, we take that exponent of the variable and increase it by a power of 1. So then, did that answer your question with the variables? Because really, we don't say with negative 2, it doesn't have variable. It's just to the 0 power. Anything to the 0 power is 1. So it's negative 2 times 1. We'll just say negative 2. To the first, to the second, to the third. Keep increasing the power. Now this is nicer than a quadratic. This is a linear expression because to get x by itself, first thing we would do is add 2, telling me that 3 times x is equal to 2. So the last value of x is, yeah, it's 2/3. Because we can have rational solutions. 2/3 does show up on the graphing calculator, but we'd have to have a good eye of telling where 2/3 lands on it, or being able to guess that that's 2/3. Or we could go through our rational zeros and then check all those values to see which one lines up with it. But for this here, I do synthetic division twice. Solve 3x minus 2. I get 2/3. It's about as quick as the other methods. Questions on this here? So that is the review sheet. If there are others that you guys want to see done or work, as you're going back through it and checking, the full review video is already up. I did every single one of these, so they are up there. You can watch that. Part 1 is 2 and before